Hello. In the previous video, I had already talked about nucleophilic substitution. This is a little bit in more detail. Few points were left in that. So, nucleophile, as we know, is an electron-rich species or electron pair donor. Okay, so the nucleophile must have an electron pair to donate. That's the role of the nucleophile. Examples of nucleophiles we had seen the neutral examples as well as the negative ions examples, which you are supposed to know. So better memorize, remember those examples. We'll see the examples of the reactions. So three reactions I have written here. This is the halogenoalkane because as we had learned in the last reaction that a nucleophile will substitute a halogen in halogenoalkane. That's what will happen. A nucleophile like OH minus, Cn minus, NH3 will substitute a halogen, which is bromine. I have taken example here, in halogenoalkane. So this is halogenoalkane in which the halogen is substituted by the nucleophile. This is what happens in the nucleophilic substitution reaction. So simply the OH minus will replace Br, Cn minus will replace Br, NH3 will replace Br. But the byproducts may sodium, OH minus come from alkali like sodium hydroxide, potassium hydroxide, etc. So here I have taken sodium hydroxide. So bromide that leaves will go with that sodium to form that this actually is sodium bromide. Similarly, the cyanide here will be potassium cyanide. So bromide that will leave here will be with the potassium bromide. NH3, you may split that into NH2 and H. So this H and this Br will form HBr. And NH2 will replace that. So ammonia mein entire NH3 doesn't get replaced, substituted by only NH2. Okay, so this is what happens. The products, if the OH minus or sodium hydroxide, potassium hydroxide reacting with halogenoalkane, I get an alcohol. If potassium cyanide is reacting, then I get a nitrile, and ammonia reacting, I get an amine. So these are the products. In this, you need to know this curly arrow thing. So how is the electron donated? Like how the movement of electron basically, electron pair ka movement. So OH minus, Cn minus being nucleophiles, they will donate the lone pair of electron. So these are the lone pair of electrons that you need to show which are being donated. So OH minus mein O has that, and nitrile and ammonia mein nitrogen has those lone pair of electrons. In the halogenoalkane, the bond between C and Br, this particular bond is a polar bond. Bromide being delta minus and this being delta plus. So here what happens is that the bromine will take both the electrons. So that is taken as shown as this. This is a heterolytic fission. Heterolytic fission matlab when this bond breaks, both the electrons taken by bromine, the carbon gets now. Which means carbon is losing the electron, it's becoming a positive ion. Similarly here, same thing. So bromine is losing the electron, bromine is gaining the electron, and carbon is losing the electron. So this is the one arrow that you need to show, this arrow. From the CBr bond to Br. Now because this carbon atom has lost electron, the nucleophile will offer an electron pair to him. So the next curly arrow should be from the nucleophile to the carbon. This way. Okay, this is what you should show in your explanation. Okay, now you need to identify three species here, which is the nucleophile, which is the electrophile, and which is the leaving group. Okay, now the nucleophile here, as we know that it's OH minus, Cn minus, and NH3. Leaving group is bromine. The halogen is the leaving group that is leaving, and in the place of that, the nucleophile is coming. Electrophile is this entire alkyl group with this carbon which has lost electron. So I have shown that as this, and there is no bond I have shown here. Instead of that, I have shown a positive charge. So that's the electrophile because this is electron deficient. He is an electrophile. Also, he accepts the lone pair of electrons. So that also makes him an electrophile. Okay. So these are the all details you should know about nucleophilic substitution. All right, the next is electrophilic addition. So as we have learned earlier in the previous video, that electrophile is an electron deficient species, or it is electron pair acceptor. Okay, in the previous example also we had seen that. And examples of electrophiles also we saw, which you need to remember, the neutral electrophiles as well as the positively charged electrophiles. Reaction wise, you only have 3 reactions of nucleophilic addition. So electrophilic addition, where electrophile gets added. So in these reactions, an electrophile gets added to an alkene. Okay. So I've taken 3 examples here. Bromine, hydrogen bromide. This could be hydrogen chloride, hydrogen fluoride, hydrogen iodide, anything. Any hydrogen halide you can take here. I've taken hydrogen bromide as an example. And water. All that happens in these reactions is that the alkene may, the carbon-carbon double bond, the 2 carbons which have double bond between them, one bond breaks and the carbon-carbon double bond becomes single bond. Then the 2 atoms here, 2 atoms of bromine, one will get added here, one will get added here. Okay, one bromine atom goes to each carbon atom, which is shown here. So you can see that this bond has become single bond and the 2 bromine atoms have been added to this. Now here, this is the electrophile, which gets added to an alkene and addition takes place across double bond. Similarly, any HBr, same thing will happen. This double bond will become single bond. H can come here, Br can come here, or alternately, H comes here and Br comes here. HL students should know that hydrogen will go to that carbon which has more hydrogens. So between these 2 carbons, hydrogen will go to that carbon which has more hydrogen. So this is 1 hydrogen here and these are 2 hydrogens here. So this hydrogen will go to this carbon. And hence, the product here will be bromopropane. The bromine will be at carbon number 2 in the propane. So this is 2-bromopropane is the major product. This is Markovnikov's rule. And the rule Excel students should know is that if H goes here, then this will become a carbocation. And this is a secondary carbocation. If H goes here, then this will become carbocation. That's a primary carbocation. And secondary carbocation is more stable than primary carbocation because secondary carbocation has a greater positive inductive effect. Okay, this is the reason that you will give. Secondary carbocation more stable because of greater positive inductive effect. Okay. The last reaction is often asked as an application. So when you add water, water should be in the form of steam because the temperature is 300. You can't have water in the liquid form there. The steam gets added and H here and OH here. This ethene becomes ethanol. So you get alcohol by this reaction. So in this video, we have seen 2 methods to make alcohol. One was in the nucleophilic substitution, where the RX, R is alkyl group, X is halogen. When it reacts with a nucleophile OH-, then OH- replaces this, and you get ROH, which is an alcohol. Alcohol can also be formed by addition of steam to an alkene. Okay, so these are the 2 reactions where we have seen the formation of alcohol. So that's all about nucleophilic and the electrophilic reactions.